Okay, we are happy to have Tom here, fresh from the airplane. He will tell us about quantum information, quantum field theory, and gravity. Please.
Yeah. Okay, can you hear me? Okay, well, I'd firstly like to thank the organizers for having me. I changed the title. I was going to talk about quantum information in quantum field theory and gravity, but then I dropped the gravity because I won't have enough time. But basically, you should understand that the motivation for all of what I'm going to be saying is related to trying to understand gravity. The other thing to say is, today I'm going to talk about these two topics. I'm going to give a lightning review of quantum information, some basic facts about quantum information, and then I'll talk about path integral methods for trying to understand quantum information in quantum field theory. And then I left the fun stuff for tomorrow so that I can sleep after the transatlantic flight and talk about algebraic methods for trying to understand quantum information in quantum field theory. And then at the end, I'll get to some applications with an eye towards trying to prove bounds on energy density in quantum field theory. Okay, so that's the plan. Okay, so let's start. So, all right, so we're talking about quantum mechanics. And quantum mechanics is an inherently probabilistic theory, so it's natural to think about it from an information point of view. We start with a Hilbert space, and we think about the most general state in quantum mechanics, which is given by some density matrix, so some rho, and this satisfies various properties. It's positive, it's Hermitian, and it's normalized. And then, we can calculate, given this, we can calculate expectation values of observables, like this. We're not so much interested in just the observables, but we're really sort of interested in the state itself. So we're interested in properties of this density matrix. There's various states in quantum mechanics. There's pure states, which look like this. And then there's maximally mixed states, which is just proportional to the identity. Something like this, where omega is the dimension of the Hilbert space. And we can characterize the difference between these kinds of states just by diagonalizing the density matrix. So if I take the density matrix and I diagonalize it, which I can do, then I get a bunch of PIs, and these PIs are all positive or equal to 0. Due to this property, they sum PAs, they sum to 1. And so they give us a classical probability distribution. Okay, so classical probability distribution, and given that, it's natural to think about sort of the information content of that probability distribution, and the natural thing to do is to talk about the Shannon entropy. So the Shannon entropy of these PIs, or these PAs, is just this minus sum PA log PA. And this tells us something about the uncertainty in the state. So for example, S is 0 for a so-called pure state, and S is log omega for a mixed state. So this is, in some sense, the state with the maximum certainty. We know the most about the state, and this is the one which is completely mixed. The other thing that we can do is that we can write this in a basis-independent way. We can write this as just trace rho log rho, and this object has a different name. It's the von Neumann entropy. But there's a new thing that happens so this I'll often denote as S of rho, or if our system, I'll call our system A, in this case is S of A, subscript rho. Now in quantum mechanics, there's a new thing that happens because essentially we can be in a pure state, right? And that's sort of the most certain state we can be in. But there are many things that we can't be certain about because of the Heisenberg uncertainty principle. So there are observables that don't commute. And that leads to, necessary uncertainty. We can not be definite about both observations of these observables. And this becomes really important when we think about subsystems. And this leads to the notion of entanglement. So, can I go here?
That's why it's fun.
I did not understand that. Okay. Why is that? Oh, because of the...
Because the camera only covers this range.
Oh, okay, very good, very good. Okay, somehow I thought that was some great real estate that I was going to use. Up. And no, you can't see that? Oh, well, okay. Okay, so now let's think about a bipartite system. So that means that our Hilbert space has some tensor factorization, HA, HB. Okay. And let's imagine that we're somehow restricted to just observations in HA. So we think about observables OA, which really I should write as OA tensor the unit operator on OB, but I'll just often just write OA. And we calculate expectation values of OA. And in fact, if we knew all the expectation values of all possible operators on HA, then we would know everything about the state, right? So we can completely characterize the state. And in fact, we can write this as trace rho over the full Hilbert space, AB, OA, tensor 1B. But then we can just do one of the traces here. We can do the trace over B. And we can write this as trace A, OA, trace B, rho. And then this defines the reduced density matrix rho A. So given some state on the full Hilbert space, then all the information, if I only have access to observables in HA, is contained in the reduced density matrix. Okay. Let's trace B, rho. And so now we want to characterize the state that we get after getting rid of HB. And so we can again define various things. We can define the von Neumann entropy of rho A, which then I'll call S of A. We can do the same thing for the B part of the Hilbert space by tracing over A, call that SB. And then for the total thing, I'll call that SAB. A simple computation in an example really shows you what's going on here. If I take a pure state in the full Hilbert space, let's say I just have 2 qubits. So this is a qubit, and this is another qubit, which is spanned by 0 and 1. And I take an entangled state, so one that can't be written as a product of some state in HA times a product of some state in HB. And then I calculate using this prescription what is rho A. I'll get something maximally mixed. Okay. So I started with a state with maximum certainty, so I knew exactly the state that I was in, and I got something which was maximally mixed. And this is a phenomenon that only arises in quantum mechanics. Now, the way to characterize it is that the von Neumann entropy of this state, you can calculate, it's log 2, and it's not 0. And so we say that something is entangled, entanglement, if and only if SA is not 0. Now, it turns out that this is true. This is the true way to think about entanglement in a system, in a bipartite system, if the original state is pure. However, if the original state is mixed, then characterizing entanglement is a much more difficult endeavor, and I'm not going to go into that. But for us, it's sufficient to know that if we start with a pure state and then we trace over something, and if we get some von Neumann entropy of the subsystem being non-zero, then you have entanglement. So this is a measure of entanglement.
Sorry.
Yes.
Here.
Yeah.
But I have a question. But if the initial state in the tensor product Hilbert space is not a pure state, then I think it is because this Hilbert space also has an environment to which the density matrix we are considering is a trace of a more general.
Sure. Yeah, that's correct. But we might be interested in whether there's some notion of entanglement between A and B, and then we shouldn't have to worry about the other system to decide that, right? And that is a difficult problem. If you talk about the third party, then actually that becomes a question about entanglement for three parties, which is similarly difficult. Now, there are answers to these questions. I'm just not going to go through them. Good. So one thing that we should note is that if I write a general pure state on the full system, then I would write something like this. I would pick some basis for A and some basis for B, and then that would define some matrix, Cij. In general, this is going to be some rectangular matrix because these don't have to have the same dimensionality. But then I can always diagonalize C using a singular value decomposition. I can use an SVD to write C as some unitary operator, some rectangular diagonal matrix, and some other unitary operator V. So the rectangular diagonal matrix is some rectangle like this, and along the diagonals, so it's 0, 0, but along the diagonals you have root P1. Where this is the dimension of HA, I think, and then this is the dimension of HB. And doing that, then you can plug this into this form, and then you get a nicer form for this state, essentially just by picking a different basis. So you use U to pick a different basis, and you can rewrite this in the following form. Sum over A. These PAs, these PIs that appear in this diagonal matrix come here. Then you have A here, and then you have A twiddle over here. So you can sort of always diagonalize this pure state between A and B, and this is called the Schmidt decomposition. And the reason that we might want to do that is based on this. We now know that the spectrum, the full spectrum of the reduced density matrix for rho A is just given by these numbers, PA. Right? Those were the probabilities that we used to define the Shannon entropy. And similarly, the spectrum of rho B is the same. Right? So they're the same. That means that they have the same entropy, von Neumann entropy. So SA is equal to SB. Okay. All right. So Good. Now, as you can see, there's sort of two ways to get a mixed density matrix. There's one way, which is to have it entangled with some other system and then throw away the other system, or to just have a mixed state to begin with. So, let's think about that a little bit. So we can have two ways to mixed rho A. Let's say our system of interest is A. One, I can have entanglement with some other system, HB, or I can just have a classical uncertainty. Maybe I'm not quite sure how the state was prepared, so forth. And a nice example of this classical uncertainty is just, the statistical uncertainty associated to a thermal state. So, for example, the Gibbs state of a quantum system with some Hamiltonian is given by this, and usually you think of that as arising from classical uncertainty. But it turns out that even if you had something that was your state was mixed because of classical uncertainty, you can think of it as this mixed state as arising from entanglement with a bigger Hilbert space. And this notion is the notion of purification. So I can always take one of these mixed density matrices and I can convert it into entanglement with something else. Purification. So given some density matrix rho A, the question is, how do I purify it? Well, it depends exactly on the specific density matrix, but you can always purify it in at most a Hilbert space, which is the same size as the original Hilbert space. So I'll call that like a reference Hilbert space. So let's take H to be HA tensor some reference where this has the same dimensionality as HA. So same dimension. There's a really simple thing you can write that does the trick. So I can just take a complete set of states in these Hilbert spaces. I can take my reduced density matrix, take the square root of it, and act on I. That's in A. And then tensor with I in the reference. And that will do the job. You can check this just by computing the reduced density matrix of that. Which I'll leave as an exercise. The trace B psi is just rho A. But there's many choices, right? So I didn't specify at all what basis. So any basis would do. In fact, I can always take any given purification, some given purification. I can take a unitary acting on the reference, any unitary acting on the reference, and I'll get the same density matrix on rho A, on A. So there's a sort of a huge set of purifications. There's a lot of freedom. Now, when people talk about the Gibbs state, there's a very natural purification that you'll hear a lot of talk about, which is the thermofield double. Thermofield double. And that will come up a lot, later on when we talk about entanglement in quantum field theory. Sort of naturally arises. that is where I just do this idea, except now I here I'm going to use energy eigenstates. Okay, so if I use energy eigenstates, then I can simply write this as just a sum over I e to the minus beta ei, that's the energy of each state, divided by square root of z. I'm just putting in the square root of the density matrix here. And then I have my energy eigenstates. Now there's a subtlety here, and that subtlety is that, again, there's a lot of freedom here. And often what you'll see is that when people write down the thermophile double using this reference, is I'll put a little star here. And what that star means is that these aren't exactly the same energy eigenstates here, but they're the ones that you get by acting with some anti-linear operator. It doesn't really matter which anti-linear operator, but just some. So let me take, EI star. You might want it to satisfy something. Well, it's nice if it commutes with a Hamiltonian, and so a natural candidate is the CPT operation in quantum field theory because that's always a symmetry. Now, why would we want to do that? Well, it makes this state much more robust. So, for example, if I rephase the energy eigenstates, EI, I can just pick arbitrary phases from my energy eigenstates. Doesn't really matter. If I go like e to the I phi I, and the rephasing can just depend on the I parameter here. Then if I didn't have this star here, this state would totally change. It would be a completely different state. So this, whereas with the star, because of the anti-linearity of T, this actually just goes to this. And so the dependence on this phase cancels out. Okay. Now you might think this is sort of a technical importance, but actually it's physically important too, and I'll try to show that. But before I do that, one thing to note about this state, this thermophile double state, is that it's invariant psi, or it's annihilated actually, by some operator, which I'll call K, which is the Hamiltonian acting on the A Hilbert space minus the Hamiltonian acting on the reference. Okay? And that's just because these have the same energy eigenvalue. So when I act here, I get the same value, and there's a minus here, so it cancels. So K psi is 0. Sorry? Say that again? Yeah. So at that point, I'm assuming H commutes with T. Yeah. So that this spectrum is the same. Yeah. Now, very good. So the other property of this state that I'd like to highlight is that there is another anti-linear operator that you can define, J. It's not quite the same as T, but its role is to exchange the different copies. And so you define it by its action on these states, and this gives you EJ EI star. And it's quite clear, so this is now anti-linear. This is anti-unitary actually. Anti-unitary. It squares to 1. It's quite clear oh goodness, wrong way. It's quite clear that J leaves the state invariant just because the form of the state, which I put up here, is invariant. So J leaves the state invariant. J psi is psi. And if J is somehow, it's associated to T because it's switching the energy eigenstates and applying this complex conjugation operation. So it's associated to this T. And if I pick T to be some local operator, so CPT in quantum field theory or quantum mechanics, the time reversal operation is local, or I can make it act locally. So for example, if I had a spin chain like this, some spin chain, this was my system A, tensor product of many different spins, and then my reference was here. And then I looked at this state that I get, this thermofield double state, as I send the temperature to infinity, which means beta is going to 0. Then what happens is you get a state which looks like this. So it's a state where you have EPR pairs that sort of line up locally. So EPR pairs. And if you didn't impose this condition, you didn't use this time reversal operation to define EI star, then you wouldn't get this in general. And so, this is nice because the reference is now somehow tracking correlations between, well, it's somehow tracking correlations in the original system in a way that preserves locality. Okay. And this is exactly the structure that we're going to get in quantum field theory. The other thing to say, is quite obvious from here is that, these are EPR pairs like this. So if I trace out the reference, then I'll just get maximally mixed states on each side. And that's exactly what happens when I take the the infinite temperature limit of the Gibbs state in this system. Okay, so that's the origin of the time reversal. Okay. So the final topic that I would like to cover in quantum, the basics of quantum information is related to relative entropy. Okay. So what is relative entropy? So relative entropy is some quantity, I'll just write it now, that takes two density matrices, rho and sigma, and it spits out a number. So it's defined as trace rho log rho minus trace rho log sigma. And what its role in life is to do is to compare two density matrices. So it compares rho and sigma. So for example, you can show, I won't do it today, I'll leave it as an exercise. You can show that, is there any bigger chalk somewhere? Tiny little chalks. I mean, I can survive for a little bit. So it compares two density matrices. So you can show this is positive or equal to 0, and it's 0 if and only if rho is equal to sigma, so equals. That gives you some notion that it's comparing two density matrices. So it only vanishes if they're the same, and it's positive. But really, there are better ways to say it. There's the notion of hypothesis testing. So the idea is that you're given some state which is rho, but you don't actually know that it's rho, and you make the hypothesis that it's sigma. And then you start measuring it, and if you make optimal measurements, then after n measurements, the probability that you would have sort of messed up your guess, so the probability that you would have had some, I guess, a false positive. So probability, something like that it's sigma given that actually it's rho. Probability that you would think that it's sigma given that it's actually rho decays exponentially. So it goes like exponential minus n. So that's the number of measurements that you make times this quantity, the relative entropy. So So that's why it's a distinguishability of two states.
Sorry, question?
Yes.
Here.
Hi.
Yeah, can you say again what is this P sigma rho? It was not very...
It's the probability, yeah, it's schematically, I don't exactly know how to denote it, so this is just a schematic notation. It's the probability that you would mistake your state for sigma, so you're assuming that it's sigma, given that it's actually rho. So you make measurements to test whether it's sigma, and then, the probability, because, all of these measurements give you statistical outcomes, the probability that you mess that up goes down exponentially.
Sorry, what does it mean, the probability that you mess that up?
Well, it's like Bayesian probability. So let's make the assumption that it's sigma, and what is the probability that it's actually rho, given that you make some measurement and you find some answer. Yeah. So you can make this precise, and I'm not defining this quantity precisely, but yeah, you can. Yeah, there is a precise definition. Basically, by making various measurements and getting outcomes that look, like the what should I say? A typical sequence of outcomes that you would get from this density matrix, the probability that would arise. Sorry, there's some precise statement that I'm going to mess up, but I can tell you what it is later.
What's the N?
Sorry.
What's the N?
That's the number of measurements. So the number of measurements that you're allowed to make. If you just make one measurement, then it's statistical. You could easily think that it's sigma.
Tom?
Yeah.
Sorry, maybe one suggestion at the physical level. I mean, you have to clearly make n of order 1 over s measurements before this exponential starts being suppressed.
Right.
And so it tells you how many measurements you have to make before you can distinguish one state from another.
Yeah, that's correct. That's what I wanted to convey, the feeling of that. But there's actually a precise sort of Bayesian argument for this quantity, which I taught a class and I gave this as a homework problem. I can give that to you if you want. Yes, yeah.
So I thought the relative entropy between two pure states was infinity.
If those two pure states are orthogonal, sure, yes.
Even if they're not, no? I thought as long as they were not, proportional to one another, you get infinity.
Is that correct? That could be correct, yeah. Okay, sorry, there's a condition here. So this is equal to infinity, and I wrote that here. If the support of rho is, and the intersection of the kernel of sigma is not 0. So these are just projectors, then yeah, that's right, yeah. Yeah, and then it's infinite, and then there is a measurement that you can make that distinguishes the two in that case.
Oh, the statement is there exists one measurement that you could make.
That's right, straight away. Yeah, I think so.
It's not just picking one random observer.
Yeah. No. You're allowed to pick your measurement. It's like an optimal measurement. Yeah. Mm-hmm. Mm-hmm. Okay. All right. Let's see. So these properties I have listed. Very good. There's another nice property of relative entropy, which it allows you to define the notion of mutual information, which you can define independently, but this gives you a feel for what mutual information is. So if I compute the relative entropy of some state, rho AB, and I compare it to rho A tensor rho B, so if I have some mixed state on the total Hilbert space, and then I compare it to the factorized state that I would get by tracing one or the other and taking the product there. Then this is actually equal to the mutual information. So it's equal to SA plus SB minus SAB, which I'll leave as an exercise again. Yeah, so this is the definition of the mutual information, but it tells you that that is sort of, it's the distance between your state is from a state which is completely factorized, like this. So a state like this has, you know, zero correlations. It has zero mutual information. So the mutual information is in that sense, measuring correlations between A and B. The other thing we can do with relative entropy is we can take a partial trace oh wow, that's a lot of chalk. Thank you. Colored chalk, very good. Okay. The other thing we can do is we can consider some Hilbert space, I'll call it HA again, which is HB tends to H some HC. And then I'm imagining I'm going to trace out C. Okay, so I start with some density matrices, and two of them because I'm comparing two. And then under the action of tracing over C, I get rho B, sigma B. And it turns out that the relative entropy of these rho and sigma restricted to BC should be bigger than the relative entropy restricted to B. So this is after I've traced out C. And this, you know, so this makes sense. In fact, you can motivate it physically because if the relative entropy is some distinguishability between two states, if I have less information to distinguish, then the distinguishability should go down. Okay, it's called monotonicity of relative entropy, and although it makes intuitive sense at that level, it's very hard to prove. And if you want to see a proof, there's a nice set of lecture notes by Witten on entanglement in quantum field theory, where he proves this sort of in generality for even for quantum field theory. Okay. And it turns out that there's actually a more general statement. So tracing over some Hilbert space is something you can do physically. You just sort of drop C. But you can do other things as well physically on a density matrix. And the most general thing you can do, you should think of as defines a quantum channel. So I can think about a quantum channel, which is just, at some basic level, a linear map between density matrix. So it's a linear map between matrices on some Hilbert space, endomorphisms of that Hilbert space, so that's just the matrix, to some matrices on some other Hilbert space. So it would take n of rho and give me rho prime, for example. And the most general thing you can do, which makes sense physically, is called a completely positive trace preserving map, CPTP. Positive is just a statement that it has to take a density, it has to take a matrix to another matrix, which is positive. Right? Trace preserving means that it preserves the norm. So those are two physical things that you would expect it to do. This completely positive is a bit more subtle. it means that this map has to preserve positivity of the density matrix, even when you entangle your state with an auxiliary system. And that's actually a non-trivial statement. But it makes physical sense, but there are channels which are positive but not completely positive. And under these maps, so a general expression for this map would be, you can rewrite it like this: sum over matrices, some row sandwiched between rectangular matrices. If this was just time evolution, right, then, so where these satisfy some property, alpha dagger should add up to 1. That gives you the trace preserving condition. And if these if this was just a unitary time evolution, if I just had an isolated quantum system and it underwent unitary time evolution, then that would be u rho u dagger, where u is e to the IHT or something. And that's a special case of this. But this operation is more like you can take some auxiliary system, you can entangle it, you can apply unitary evolution to the larger system, and then you sort of trace out the remaining part. And so that's the general thing you can do, and it looks like this. And it turns out that relative entropy, under traces like this, always goes down, but under some quantum channel also always goes down. So you get the following statement. And this is sort of the most general statement of monotonicity of relative entropy. Okay. The other thing, the other thing I want to say is some comments about relative entropy and thermodynamics. Which is actually closely related to the uses of relative entropy in the context of black hole physics, which hopefully I'll get to next lecture. But let's take some density matrix and let's compare it, just some random density matrix, and we'll compare it to the Gibbs state, this e to the minus beta h. Okay? Then it turns out we can write the relative entropy in a nice form. Let me stay here. Okay, so the relative entropy, remember, was given by this trace rho log rho minus trace rho log sigma. But what I can do is I can add and subtract trace sigma log sigma and plus trace sigma log sigma. So this is the same thing. I'm not doing anything. However, you see, what is this? This is the von Neumann entropy of sigma. This is minus the von Neumann entropy of rho. So this is just minus delta S, where delta S is the change in the von Neumann entropy, or the entanglement entropy between these two density matrices. And this guy is just the expectation value of this operator log sigma in the two different states. But log sigma is just related to the Hamiltonian, so you can easily show that this term is equal to the change in the energy of the state times beta, where the, let me just go back here, where the energy is just the expectation value of the Hamiltonian. So delta S is S rho minus S sigma, and delta E is the expectation value of H in rho minus the expectation value of H in sigma. So then you see that the relative entropy is a change in a free energy. right, where the free energy times beta, where the free energy is just Ts of rho minus the expectation value of rho. So that's F rho. Okay, so the fact that it's positive is just the usual statement that the changes in free energy away from equilibrium are positive. Okay? Now, if we take, so that makes sense, that's well known, but now if we take one of these quantum channels, take this N, this noisy quantum channel, which now acts on density matrices, and let's take it to act on density matrices of the same dimension, so it maps between density matrices of the Hilbert space and that of the same Hilbert space. And additionally, if we assume it has the property that it preserves the Gibbs state, so it leaves invariant the Gibbs state, then you can still calculate the new relative entropy under the action of this noisy channel, of this quantum channel, using the same idea here. And you find that delta F should be bigger than delta F prime. So prime is the n of rho gives rho prime. So that's after the action. But the original free energy is the same as the free energy of the Gibbs state, so that just means that F is bigger than or equal to F prime. Right, which is the statement that the free energy is decreasing, which is a statement of the second law of thermodynamics. This is the second law of thermodynamics. Of course, it shouldn't be possible for me to derive the second law of thermodynamics because it's really only, if true, it's really only true in some statistical sense, and so it all comes back to this assumption. I'm picking a channel that keeps invariant the Gibbs state, and that's non-trivial. That's not always going to be the case. Okay.
Sorry. So you're saying that what?
Yes.
That what? Yeah. That noise operator leaves invariant. What do you mean by that symbol? I mean.
The N?
No. Yes. What's that?
Sigma. Sorry.
Okay.
It's the same thing. So the sigma is the Gibbs state. So it's this, this state here. Yeah. Okay. All right. Okay, good. So, all right. So that's the end of the lightning introduction to some concepts in quantum information that I'll use. And so now I'm going to talk about quantum information in quantum field theory, more specifically. And so before I get to the just talking about the path integral methods, which is what I'm going to talk about today, let me make some general comments. So I think the motivation or a motivation for studying quantum information in quantum field theory is that it's just a new way of looking at an old subject, I guess. But we're used to computing correlation functions, 2-point functions, 3-point functions, so forth. Maybe we're interested in S matrices, or whatever. And that's okay, and we can study specific models, we can compute correlation functions in specific models, but it's also nice to try to make some general statements about correlations in quantum field theory. And so from that point of view, we should really think about quantum field theory from some information perspective. So rather than speaking of specific correlations, we might study something like the mutual information, which tells you about somehow all correlations that can arise. So that's one motivation. The other motivation is that it works. There's many powerful results that have come out of this. The classic, so many powerful. The classic ones that I think is really important is that it has given us information on RG flow and trying to find RG monotones in quantum field theory. It turns out that you can do that with quantum information. It constrains the dynamics of the theory in interesting ways. And something that I'll talk about later is that it gives us a connection to energy conditions. And I think Raphael gave a talk yesterday where I'm sure he mentioned energy conditions. So you know what that's all about. And this list is not at all exhaustive, but there's many results. And then, of course, there's the big one, which is ADS-CFT. So the idea here is that studying quantum information in quantum field theory, it's the building blocks of the correlations in the quantum field theory, and it maps under the ADS-CFT duality to the geometry, the building blocks of the bulk, which is geometry and gravity. So there's some fascinating relation between quantum information and gravity. It doesn't just have to go via this ADS-CFT duality, although I think that's what's underlying a lot of the connections between these two. Okay. So, so I'm going to study two technical approaches to this problem. One is the path integral. And the other one is sort of algebraic methods, which are old methods that have, I think, starting to be more and more used because I think we're sort of realizing that this is really the language that we should be talking about quantum information in quantum field theory using this language. Okay. Good. Are there any questions? Other way. Questions? Okay. Oh. Okay. So what should we expect? So firstly, we're going to look at correlations. And one thing that is interesting is to build in locality to those correlations. So we're going to think about trying to split the Hilbert space in some way that respects that locality. So what subsystems should we examine correlations for? So it's useful to at least begin by thinking about some lattice regularization of quantum field theory. So we would have some lattice like this. I'll just draw a one-dimensional lattice where the total Hilbert space is just some giant tensor product on each of the lattice sites of some Hilbert space for each single site. So this is H1, and so forth. And then the Hamiltonian will interact between these two. And then there's some lattice spacing, which I'll call epsilon. And so given this structure, then it's natural to just split the Hilbert space locally here. So we'll pick some lattice sites, maybe these four, and we'll call that A. And then everything else, I'll use the notation, instead of calling it B, I'll call it A complement. Okay, so that's some bipartite split of the Hilbert space. This is true. And then we can try to calculate entanglement entropy and so forth. Of course, I have to pick a state before I do that. Before I can calculate anything, I need a state. So the entanglement entropy depends on your cut, but it also depends on the state. Often, maybe that's not said explicitly, but often it's the ground state of some Hamiltonian, of some local Hamiltonian. And so sigma is this guy. And then, you know, let's calculate, say, S of A for that state, for sigma. Now, we can just do that, right, for a lattice system. We could do that on a computer, say. But maybe we're interested in the continuum limit, and we're interested in the continuum limit where we get relativistic quantum field theory. So that's a subtle thing. We need to find we have to find a right model which does that, and we have to be able to take a continuum limit of that model. And in particular, you know, it's nice if we have some kind of critical point, some quantum critical point with relativistic symmetry, quantum critical point, and then, you know, as long as the cutoff, the lattice spacing is much, much less than our correlation length, then maybe we're probing properties of some relativistic quantum field theory. Now, when you do this, if you were powerful enough to do that, then and calculate the entropy, then you would find an answer which is infinity. So you would calculate this guy, and you would get something that looks like the area of the boundary region divided by epsilon to the d minus 2. So I've only drawn one dimensions here, but it's not hard to think about what happens in higher dimensions. I have some A complement, and I have some lattice regulator. This is epsilon. And as I send epsilon to 0 here, I'm going to get some infinite answer like this, which is proportional to the boundary of the area. Okay, so what that's telling us is that at least in these specific states, ground states of local Hamiltonians, we're getting large amounts of entanglement between constituents that live at the boundary. Okay, this is some UV entanglement, at the boundary of the region where you're cutting the bonds. Okay, now it turns out that you can argue that actually all low energy states, which is really what we mean by the continuum. So when we take the continuum limit, we have to pick a special class of states. We can't just pick any state. We can't have states, say for example, you could have a thermal state where the temperature is of the scale, 1 over the scale of the lattice spacing. So we can't, we're not going to think about those states. We have to throw them away. So when we talk about quantum field theory, we're talking about some specific low energy states. And it turns out you can argue that all of these states have this area law. So they have all the same universal entanglement structure. Have same / or universal entanglement structure. Okay, so there's several ways to deal with this problem. Well, maybe it's, depending on who you talk to, it's a problem or not. But let's say we're not really so interested in this, which is somehow related to how you regulate the theory. We're more interested in some properties of the theory itself. How would we extract that from entanglement entropy-like things? There's several ways. Those states that are governed by quantum field theory, yeah, that's what I would say. Yeah. So this was in quotes because from the lattice point of view, I'm not totally sure how to do it. But what I really mean are just the states that are governed by continuum quantum field theory. And then we can make statements about the universal entanglement structure of those states. Yeah, I think that it's an interesting question how to do this in the lattice. But yeah, so one thing we can do is we can say we're not interested in this. Let's just subtract it away like we usually do in quantum field theory. So we somehow renormalize this quantity. It's a UV divergence, so we renormalize it. And let's say we're interested in some subleading term that's nice. So that's one strategy, is we should just subtract the divergences. And some subleading answer, which is somehow, more related to the quantum field theory of interest. And a simple way to do this, this strategy, is to just take two states. Say one is the vacuum, one is some excited state, and you take the difference. And in many cases, not all cases, but in many cases, all of these divergences cancel. There are other divergences that arise here, by the way. And then this is just some universal quantity. This works. Sometimes there are some exceptions to this. Another one is to think about the mutual information between two regions that are disjoint. So let's say I have A, and then B, and then I have everything else. Then remember this quantity was this. And since these divergences are somehow local to the boundary, you would expect that there is a divergence of SAB, which is again local to the boundary, which is the same as the divergence of SA and SB separately. So somehow there's some, let me draw it over here, some A, some B. So there's some divergences here, some divergences here, but then they're subtracted by the divergences here, and then this is meant to be finite. And indeed, you can do specific calculations where that's the case. Then there's the final another option is to calculate the relative entropy. And it turns out that the relative entropy actually has a very robust continuum limit. It's a little bit like this, but it's better. And the reason for that is that there exists a continuum definition of this quantity. And I may or may not get to that tomorrow. So there's a definition of the relative entropy which works and doesn't even see any of these divergences. Okay? Yes?
Is there any connection between the continuum definition and this definition?
Between the original definition and the...
Well, the continuum definition, I guess, using on the rate quantum.
Yes, yeah.
And this kind of definition?
Yeah, well, I mean, yes. I mean, in the sense that the continuum definition is sort of a definition that works in general for all kinds of algebras, which I'll get to tomorrow, including that algebra. So, and it reduces to that. So, yeah, that's the connection. Yeah.
Since this is a UV divergent, is there some kind of Wilsonian interpretation of effective field theory that we could give here, or is just canceling infinities?
Yeah, so there's some kind of, yeah, so that's a really good question. The answer to that is that there is, but it involves adding gravity in some weird way that we don't fully understand yet. But it turns out that if you take this and you add it to the Bekenstein-Hawking entropy for this area, for this surface, imagining it's a black hole for some reason, then in certain situations there are divergences here and there's divergences in G Newton that cancel each other, and then you can talk about some Wilsonian you can talk about the RG flow of that quantity. Yeah. So there is a, yeah, but it's sort of, I don't think we fully understand that. Yeah.
Tom?
Yeah.
When it's a good time, maybe you can do 5 minutes break between the two parts.
Ah, okay. Is that what we do? Okay, good. Yes, yeah. Yeah.